This video, we're going to talk about some exponential growth problems. We're going to do a couple with exponential growth, exponential decay. We'll do a half-life problem, and then we'll also do a compound interest problem. This problem here, the table shows the number of trucks registered in a city each year. Suppose the growth continues exponentially. How many trucks registered in the city in year 9? Round to the nearest whole number. All right, we'll start off with our formula. Y equals B 1 plus R raised to the t power. B is your starting or beginning amount, t is the time, R is the rate as a decimal, and Y is the ending amount. All right, what we're going to do first is see if we can figure out the rate of growth each year. And we can do that by putting in 110 for Y. We'll use the first value here to kind of figure out our rate. We're going to put 110 in for Y. The beginning amount is at year 0. That's where this 100 is. And then we're trying to figure out what that R is. And this is going to be raised to the 1 power. So I'm putting a 1 in for t here. All right, we're going to divide both sides by 100. And 110 divided by 100 is 1.1. And then 1 plus r to the 1 power is just 1 plus r. And then all we got to do is subtract 1 from both sides. And then it tells us our rate of growth, 0.1. So we have r by itself. This tells us the rate. All right, now that we know r, and we also know the initial amount, the 100, we can plug in any number for t, any number of years, and it'll tell us the ending amount. So let's do that here for year 9. So we're trying to figure out an amount. Y equals 100, the starting amount. One plus the rate. So 1 plus 0.1. And then we're raising that to the 9th power. All right, so calculator, all you need to do is put 100 times 1.1 raised to the power of 9. And it's going to spit out, I believe, 235.8. And they want us to round it to the nearest whole number. So if we have 0.8, this will round to 236. The approximate is. All right, and this will be how many trucks should be registered in the city about in year 9, 236 trucks. All right, look at another one here. On an island is declining at a rate of 1.4% per year. The population was 3,800 in the year 2009. Which answer is the best prediction for the population in 2014? All right, well, for exponential decay, y equals b. This time instead of 1 plus r, it's going to be 1 minus r. And raised to the t power. All right. So our initial amount is 3,800. And of course we have a 1 minus the rate being 1.4%. As a decimal, that's 0.014. And then we're going to raise that to the fifth power because we go from 2009 to 2014. That's a difference of 5 years. We put all this in a calculator, exact as long as your calculator has a parentheses and an exponent button. 3,800 times 1 minus 0.014 raised to the fifth power. Round to the nearest number, 3,541 is what it comes out to. It might be rounded here based on what your calculator says. Notice that's a decrease from the original population, and it should make sense. If we start at 3,800, should be a number lower than that, which it is. And so this should predict the turtle population after 5 years. And this one, year 2005, we're a total of 750 fish introduced into a man-made lake. Fish population expected to grow at a rate of 8.3% per year. What will the fish population be in the year 2050? Round to the nearest whole number. All right, we're going to use our exponential growth problem. Amount is the B value, 750. All right, 1 plus the rate, 1, I'll just add it automatically, 1.083, because that's the result of adding 1 plus the decimal of 8.3%. And then the exponent is the amount of years that went. If we go with 2005 to 250, that's 45 years. And if we substitute that into our calculator, make sure your calculator has parentheses and an exponential ability, rounded to the nearest whole number, fish population should be approximately 27,123. Problem. The element sodium-24 has a half-life of 15 hours. How many grams of a 900-gram sample remained after 90 hours? Okay, here's our formula for half-life. A little bit different than exponential growth and decay. It's going to be somewhat similar to the exponential decay formula. Of course, we're going to have B, our initial amount. Call it a half-life. That is the base of the exponent we're talking here. So the fraction 1/2 or the decimal 0.5 can go in the parentheses here. Basically our rate of decline, whatever is left, it is declining by half that amount every cycle. And then the exponent is our time, but the time is going to be divided by h. H being standing for the half-life. All right. So we're going to sub in all our values here. Time being 90, and then the half-life itself is 15. So if we simplify this just a little bit, we still have the 900. "90 divided by 15 is 6. All right, and then we're going to substitute this into a calculator. 900, multiply it times 1/2, and then you want to raise the 1/2 to the 6th power. And we're going to put all the decimals to be as accurate as we can when dealing with half-life problems. We always want to be as accurate as possible. I'm going to have 14 grams. Problem. We have a situation where after 5 years, the total amount of a compound interest investment was 32,000, 3% interest, and we compound it quarterly. We want to know how much is left if we wait 5 years and we compound it 3% quarterly. So here's the formula we use. Our current amount is the P principal, the starting amount, 1 plus the rate divided by the number of times we compound it, raised to the power of the number of times of compounding times the number of years. All right, so we'll put in our value, 1,000. The rate is 0.03. We're compounding it quarterly. That's 4 times in a given year. And then 4 times to the number of years, the exponent of 5 years. We can simplify this a bit. 3 divided by 4.0075. We're adding it to the 1, and the 4 times 5, giving us 20. 32,000 times 1.0075 raised to the power of 20 comes up to $39,000, 157 and 89 cents. That is all. If you have any questions over these problems, feel free to comment below. Thank you for watching.